Okay, everybody. So what we're going to be looking at today is just going to be kind of a review of integration. And so we're going to be talking about definite integrals, which we covered recently, and we're also going to be going back and talking about um, what are we going to be talking about? Indefinite integrals. And the reason we're going to be doing that is just because you kind of have to be solid at the basics of integration before you go on and do substitution. So I hope you guys will watch this lecture and get something out of it. Okay, so let's just kind of summarize what you're supposed to know. So let's start with indefinite integrals. So indefinite integration. What are you supposed to know for that? So the basic formula is this. You have an integral. There's no limits of integration. So there's nothing down here and there's nothing up here. And then you've got a function. And then the result is going to be a capital F of x plus c. And this is where the capital F is going to be the antiderivative of the little f. Okay? And so any integral of this type where there's no limits of integration is called an indefinite integral. And in order to solve these, you need to be familiar with all of your rules for antiderivatives. So you would want to know your common antiderivatives. Now this is in a worksheet, not a worksheet, what's it called? A handout, right? We'll say from common derivatives and integrals handout. Now, I'm not looking at that handout, so these aren't going to be in the same order or anything like that. But they're going to be the same functions because everybody, every class like this covers the same functions. So what are some of them? So we'll write them in the integral symbol because we know that the integral symbol means the same thing as an antiderivative. And, we know that if you have x to the n, that you're going to do this with the power rule. So I'm going to write it here, x to the n plus 1 over n plus 1 plus c, where c is a constant. Remember that for derivatives, right, you had a different power rule. For derivatives, the derivative of x to the n was nx to the n minus 1, right? But this is a derivative rule. This is an integral rule, right? So derivative rule, right? Which is not what we're doing today, not what we want today. Okay, we want the antiderivative rule, the rule that undoes the derivative rule. So we want the one on the left. Okay, now that's just one of them. Now you need to know that. Normally we don't make a big deal about this, but if you ever are integrating just a constant, I'll even write it a couple different ways now that I think about it. But like if you have just an integral of dx, and I don't know why I'm writing that, but if you have an integral of dx, that's just going to be x. And in general, if you have an integral of a constant dx, then your result is going to be kx plus c. Okay, so those are easy as well. Now I want to say something up here about number one. Got to. You may have noticed that there's a problem here, and that the problem is what if n is -1? Because if n is -1, then -1 plus 1 is 0, and you're dividing by 0. So this formula here is actually not good 100% of the time. It's only good when n is not -1. Okay. Now, it's officially in Math 4B, not Math 4A. So technically, this is not part of this class. However, with the homework system that we're using, Newton Alta, it's very difficult to avoid these problems. So I'm going to write it here anyway. which is going to be what to do if n is equal to -1. So let me get the red color again. If n does equal -1, then what you're going to be looking at is the integral of 1 over x dx, right? Because if n is -1, that's x to the -1. X to the -1 is also written this way. Now, what is that one? Well, we did not learn it. Okay, we didn't learn it in this class because it's part of 4b. But if it comes up, you get a natural log there. And I'm not going to prove that right now or anything like that. I'm just going to write it here just in case it appears in the homework or something. If it does appear in the homework, shoot me an email and I'll do a better lecture on this, okay? But that's one that you might need to know. And then after that, it's mostly just the trig functions, which there's a separate rule for every trig function. Not every trig function, every derivative that you learned for a trig function has a backwards formula, right? So like, let me get the red again. Like you learned that the derivative of the sine function is a cosine function, right? And you learned that the derivative of the cosine function is the negative sine function, for example. Also, something that's I think is a much better way to memorize this, by the way, so I'm going to do it this way, is if you had the derivative of sine kx, where k is a constant, due to the chain rule, you would get cosine kx, and then you would have to multiply by the k for the chain rule. Right? You remember the chain rule, don't you? Not too long ago. So, right, as an example, if you did the derivative of like sine 3x, it's just 3 cosine x. Sorry, that's not right. That's not right. Hold on. 3 cosine 3x. Right? It's cosine 3x, and then because of that 3, the chain rule makes you multiply by the derivative of what's inside. So you multiply by the derivative of 3x, which is 3. So you end up with this extra 3. That's the k. And so when you're learning your backwards formulas for your antiderivatives, it is really nice to memorize them this way. So like when I'm going to be doing the antiderivative of, I'll do sine first, sine kx, well, maybe I'll write them both. I'll write them both. If you're doing the antiderivative of sine x, then it's the backwards formula. So it's not this one, it's actually this one, because you're starting here and going backwards. And so you end up with negative cosine x plus c. That looks backwards, right? Because the derivative of sine is cosine, but the antiderivative of sine is negative cosine. Because technically it's not this line that we're looking at, it's this line that we're looking at. All right. But while I'm writing it, if you want to put a constant in there, kx, also I forgot a dx on this for some reason. Let me fix this. Dx. If you are integrating sine kx, what's the k do? Well, it's basically the backwards version of this formula. And because you're going backwards then, if you go in left to right here, you multiply by k. If you go right to left, you would have to divide by k. Because this has a k, this doesn't. So backwards, you'd have to get rid of the k, which would mean dividing by k. So the formula would be negative 1 over k cosine kx plus c. So you just end up with this 1 over k. Or if you want to write it this way, cosine kx over k, negative plus c. So of course, those are the same thing. You can write it whichever way you want. All right. Now, having said that, there's not much point in writing this first line if you're going to remember the second line, right? What to do with the k. So I suggest memorizing this kind. So let's write the others. I'm not going to write that many lines for them all, but let's do antiderivative of cosine kx. Well, antiderivative of cosine is sine. So you can write it negative 1 over k sine. I wrote a negative, but no. Sine kx over k plus c. No negative on that one. Sine and cosine were the easy ones. You should remember that the derivative of tangent is secant squared. So that means that the antiderivative of secant squared, and again, I'm going to go kx, is the tangent, but with this 1 over k. And what else did we know? We know that the integral of secant x, kx, I'm going to have to do kx, tangent kx dx. Well, you should recognize secant x tangent x as the derivative of the secant function. So that's 1 over k secant kx. We did secant, we did tangent, we got cosecant and cotangent, and that'll be it. So antiderivative of cosecant, said it, didn't write it, cosecant kx is going to be 1 over k negative cotangent kx plus c. And then finally, we got cosecant cotangent. Cosecant kx cotangent kx dx is going to be 1 over k, and this is the derivative of the cosecant. At least it is if you put a minus sign on it. There you go. All right. So we got the sine, cosine, tangent, secant, cotangent, cosecant. A, B, C, D, E. Okay, that's 6. All right. So really, these are the formulas that you need to know for your common antiderivatives. So all your trig functions, right? One for each of the normal trig functions, but it's a backwards formula, so this is a little bit different. And the power rule, and that's basically what you need. And you shouldn't need this, but you may. So that's those are the basics. Now, what are you going to do with them? We're going to remember how to do some examples, right? So let's do a few examples to remind us. So let's say we have an integral of, let's just start simple here. Let's go, well, not too simple, I guess. Let's go t squared plus sine 3t dt. Okay, and then parentheses. Right? So, of course, you should notice certain things about this. The dt is telling you the variable's t. That matches this t and this t. That's all fine. Also, the dt is technically on both of these because of these parentheses. It's always going to be like that. And what do we do here? So formally, I'm not actually going to use this, but I'm just going to write it. Formally, you can break this up into two different integrals like this. Right? I didn't write down the properties here, but we know that you can break an integral into two integrals, and then you do this integral and this integral separately. But I don't really write it like that. I just think it like I'm going to take the antiderivative of t squared. I'm going to take the antiderivative of sine 3t. Okay, that's how I think of it. So I don't write this, but that's the rule that you're applying. Okay, so let's actually find these antiderivatives. So here you've got t squared. So using our formula here, right, power rule, we're going to just add 1 to the exponent, right, whatever n is, add 1, and then that power goes in the denominator as well. So we add 1 to the power, so the 2 will go up to 3, and then we're dividing by that new power, so it goes down there. Easy peasy. Go plus. Now we've got the antiderivative of sine 3t. Well, that is one just like this. So we know that what we're going to have to do is it's going to be 1 over k, negative 1 over k, cosine kx. So the k is the 3. So we're going to have an extra negative sign because sine to cosine is going to give us a negative. So we're going to go negative 1 over k. The k is 3, right? There's your k. 1 over 3 cosine 3t, right? It's a t because that's what our variable is. And that's that antiderivative. And then you just put a plus c on the end. Right? So this isn't that bad, right? It's just antiderivative, antiderivative. Okay? Example, what are we going to do here? Let's say, what are we going to do here? Oh yeah, so they like to trick you. You might remember these where they give you something designed just to be annoying, essentially. I mean, no, it's not really designed to be annoying, right? It's designed to make you simplify it. So if you look at this right here, I'm going to change this to a 4, actually. So if you look at this right here, then you should realize that this is not something that's on your list, right? You can do an individual exponent. You can't do a big mess of algebra, okay? So you need to recognize that this is just not on our list, not on the list of antiderivatives. So you have to simplify it. That's a clue that you need to simplify. Okay? And this would just be using normal rules for algebra that you're already supposed to know. So in this case, you would split this into 2 fractions, t to the 4th over 3t, right? There, that's over 3t. So t to the 4th over 3t and t to the 1/2 over 3t. Like so. From there, that's better. But then we need to simplify these exponents. So you're just going to apply basically this rule, right? Like if you've got, a to the b over a to the c, that's a to the b minus c. So subtract those exponents. So on this first one, we've got, first of all, the 3 in the denominator. I'll just write that 1/3 out to the side. And then t, what's the exponent going to be? Well, you subtract. So the b and the c, b minus c. So we have a 4 and a 1 because we don't have an exponent written here, so it's a 1. 4 minus 1. Okay? And then for the other one, same thing. There's still a 1/3, right? It's 1/3, not 3, because the 3 is in the denominator. And then for your exponent, top exponent is 1/2, bottom is 1 again. Like that. So you have an integral 1/3, and that's t to the 3, plus 1/3 looks like t to the negative 1/2 dt. Now at this point, this is on our list of antiderivatives because these are power rule problems. Now we use the power rule, which was the first one up here, right? This is power rule. So we're just going to add 1 to the exponent, divide by the exponent. Just like we did on this one, right? Just like we did right here. 2 goes up to 3, divide by 3. So when we do that here, we're going to have the 1/3 is just along for the ride. And then what about the t? Well, t to the 3. So we add 1, get 4, divide by 4. That's it. Go to the next one. We've got the 1/3 again, t. Add 1 to the power. So negative 1/2 plus 1. So negative 1/2 plus 1 is positive 1/2. And then we're supposed to divide by positive 1/2. Okay. And then plus c. Now, all we have to do now is just kind of make this look a little prettier. You could type this into a computer and it probably will be fine. But let's make it look a little nicer. So we can multiply across here. So 1 times t to the 4, 3 times 4. So on top, t to the 4. On the bottom, 3 times 4 is 12. Now here, you have to be careful. I don't have to be careful, but when you divide by 1/2, that's the same thing as multiplying by 2 over 1, right? Dividing by a fraction is multiplying by the reciprocal. So then what you want to do is just combine those fractions. So 1/3 times 2 over 1 is 2/3. And then t to the 1/2 is fine. If you want to, you don't have to, but if you want to, you can rewrite that as a square root. And that is what your answer would be. Okay, so hopefully you remember these. I think you've done them pretty recently anyway in the section on definite integrals. But that's how these go. You mostly are going to see ones that you have to simplify like this, or ones that you don't, and you can just do them directly. Now, this is from antiderivative, so this is a while back now. So when I just said you're going to see ones that this is how you do them, that's actually not quite true, right? Because what you have coming up is substitution, and substitution is a technique we haven't learned yet. So you're not going to do it like this. You're going to use substitution. Okay, let's go definite integrals now. So definite integrals are what we just covered, but I want to talk about it specifically with regards to how it's different to what we just did above. So definite integrals were written this way: a to b little f of x dx typically. And remember that the way you solve them is you still find an antiderivative. You still find an antiderivative, but you keep these limits of integration, the a and the b, and then you plug those in and you get f of b minus f of a. And this right here is one version of the fundamental theorem of calculus. Okay, so this is fundamental theorem of calculus. Okay, so the steps are a little bit different. You're still finding the antiderivative, but after you find the antiderivative, you've got to plug in the b and plug in the a and subtract. That's the difference. Okay, so let's go up here, for example, and pick one of these. So like, let's say I have this same, well, I don't want to write it that way. Let's say I take this integral right here and I cut it out like so, duplicate it, let's come down here, and let's have this be our first example of a definite integral. And I'm just going to put some numbers on here. So let's just go 1 to 4. Okay, so if this is your integral, then what you would have to do is your first step is going to be find the antiderivative. Okay, so you have to do that according to the rules. So we know how to do that, right? We know how to do that. We just did it. So you're going to add 1, to the exponent, t to the 4 over 4. So we have 1/3 t to the 4 over 4. Here you've got 1/3 antiderivative of t to the negative 1/2. We just did it. T to the positive 1/2 over 1/2 from 1 to 4. right? So the only thing that's new is you put the 1 to 4 there, and you don't put the plus c. You don't need the plus c. So let me simplify this again. Whoa, I did not do that. It just scrolled on its own. Okay, so what were we? T to the 4 over 12 plus 2/3, and we had it written square root t, right? Didn't we, when we simplified it? I think so. All right, so this was what we got for our antiderivative. After you have your antiderivative, then you just have to remember to do your, you know, f of b minus f of a thing. Okay, so let's do that now. So parentheses, we're going to put in a 4 for all of the t's. So 4 to the 4 over 12 plus 2/3 square root 4 minus, and then you're going to put in the 1. So you put the 1 in for the t's. So 1 to the 4 over 12, exponent 4, plus 2/3 square root 1. Okay, so this was, right, this was f of 4 right here, and then this is f of 1. That's what's going on. So then you work this out. So 4 to the 4, 4 to the 4 is what? I don't know. 16 times 16, I can't do that. Is it 256? I feel like it's 256, but I don't know. So let me grab a calculator here. That'll work. That's almost a calculator. 16 times 16. Or 4 to the 4. Yeah, 256. So this is comes up 256 over 12 plus 2/3 times 2, because I'm doing the square root there. Be careful with your minuses. This minus is on this whole thing. So minus 1 over 12 plus 2/3 times the square root of 1, which is 1. What's 256 over 12? It's going to be a fraction, but 256 over 4 is 64. So this is 64 over 3, I think, plus 4 over 3 minus 1 over 12 minus 2 over 3. Okay, so you have this. If you have a calculator that does fractions, I would recommend that you use it here for something like this. If you don't, then use wolframalpha.com, right? Something like that. Just something you can type it in. Because I'm just going to type in 64 over 3 plus 4 over 3 minus 1 over 12 minus 2 over 3. And let the computer do that for me. And I'm going to get a number which is 263 over 12. And that's my answer. Okay, so this is computational work, but the actual calculus stuff is finding the antiderivative. This isn't that bad. It's just working through the numbers. Okay, let's do another one. Something I think they didn't give you a lot, I wish they had, but they did not, was problems with trig functions. So like something like this, we should be able to do, let's say an integral from, let's go 0 to pi over 4. And trying to come up with one that's not going to, a function that exists everywhere, so we don't have any issues. So I'm going to say, let's go sine. I'm going to go 3. Let's go 3y, just to change the variable. Let's go plus 2 secant. I think that'll work. 4. Wait, 4. If I do 4y, no, let's just do 2 secant y, tangent y. I think that'll be okay. Secant 1 over cosine, not defined at pi over 2. It's fine at pi over 4. Yeah, that's fine. Okay. Yeah, let's do this. Okay, let's do this. So here we go. We've got another indefinite integral. And all you're going to be doing here is you're going to be finding your antiderivative, same as before. So find antiderivative, and that's using your basic rules for antiderivatives. So you're going to be looking up the antiderivative of sine 3y way up here. So like if you're doing sine, ooh, I just erased that. If you're doing sine, sorry, I can't see my screen. Let me go back. Okay, sorry. If you're doing sine 3y, write your k as 3. Then your result is going to be here, negative cosine 3y over 3. Right, k is 3. So we're just copying the formula using our variable. So we have a negative cosine 3y. The 3 makes us divide by 3. There's my antiderivative. Same sort of thing here. We've got secant y tangent y. We come up here, we recognize that. Secant tangent, same thing inside kx, kx. That matches this one. So the result is going to be 1 over k, secant kx. Our k is 1 because we actually don't have a coefficient here. But that's fine, you don't need one. So we've got this 2 along for the ride, so just 2. And then when you see secant tangent, you say, what's the antiderivative of secant tangent? Well, that's secant. That's what we're looking up. So what's the result? Secant y. Should be secant ky over k. K is 1. All right. And then you've got your limits of integration still. After you do that, you got to do your f of b minus f of a, which means plugging these in for the y. So we end up with, parentheses, negative cosine 3 times pi over 4 over 3 plus 2 secant pi over 4, parentheses, minus, then we got to plug in the 0 for both of the y's. We get negative cosine 3 times 0, which is 0, over 3, plus 2 secant 0. All right? And from there, we're just going to work out these numbers. So this is going to be, this is going to be cosine 3 times pi over 4, 3/4 pi, like that's going to be, I'm just going to write it out. Cosine 3 pi over 4, 3/4 pi over 3. Secant pi over 4, that's fine. I'm going to distribute this minus. So this is minus minus, which is a plus. Cosine 0 over 3. 3 times 0 is 0. And here, minus the plus is going to be a minus. It's going to be 2 secant 0, whatever that is. Okay, so I haven't done any trig yet. Okay, so let's actually solve these. If you have a calculator that will work through these symbolically, good. I don't right here, so I'm going to have to do these by hand. So I'm just going to draw a very small portion of the unit circle. Thought I was going to do a half circle. I did not. Cool. Whoa. Okay, cool. That's better than it needed to be. All I need off here is a couple of points, right? That's pi over 4. We're going to need that one. Coordinates here are root 2 over 2, root 2 over 2. Of course, I need this one, 0 degrees, 0 radians, which is 0, 1. That's not true. 1, 0. Okay. So I've got the 0 for these. I got the pi over 4 for this, and 3/4 pi, which is over here. Oh wow, I didn't know that it could do arrows. That's neat. Weird. I had no idea. Okay, doesn't matter. Point is that coordinate right there is going to be negative square root 2 over 2, positive square root 2 over 2. All right, so having done all that, we should be able to work these out now. So I've got negative over 3. Cosine 3/4 pi is going to be the x value here. So the x value is root 2 over 2, negative root 2 over 2. So negative root 2 over 2, like that. Plus 2 secant. Actually, we're going to work that out, so let me erase that. 2 secant pi over 4. So secant is 1 over the cosine, and cosine is the x value. So here's pi over 4. The x value is in square root 2 over 2. We want 1 over this. 1 over this, if you work it out, is just square root 2. You have to work it out, though, to convince yourself. Then we got cosine 0 over 3. Cosine 0 is going to be the x value here. So 1 over 3 minus 2 secant 0. So again, the x value is 1. So the cosine is 1. And then 1 over 1 is 1. So it's going to be a 2, because 2 times 1. All right. So we got, what do we have? Square root 2 over 2 over 3. That's square root 2 over 6. Negative, negative cancels out, so it's positive. Plus 2 square root 2. Can we add these? What's 1/3 minus 2? Impossible to say. It's not actually. It's negative 5/3. I'll just add this right now. Minus 5/3. This was done on a computer, and then we can add these. So if I'm going to, I'll just add them by hand. Square root 2 over 6 plus, if you multiply this by 6 over 6, it will be, what will it be? 12 square root 2 over 6 minus 5/3. And finally, these can be combined. So we're going to get 13 square root 2 over 6 minus 5 over 3. And that's probably as much as I would want to do. That would be my answer. Now, you could put this into a computer at any point. You could have typed this into Wolfram Alpha, and it would have calculated all the trig functions for you, and that would have been nice. But I didn't, just worked it out by hand. Okay, so that's that. And do we want to do one more? Trying to think here. Yeah, you know what? I think that's almost all I want to do. I just want to say what's coming next, and then we'll be done. So the next thing to cover is going to be substitution. And so specifically what substitution is it's going to be how to do integrals that we have no idea how to do right now, a certain type. So basically, if you had a problem like this, we would know the answer, right? We just talked about this. That'd be like negative cosine 3t over 3. And we know that because it's on our list. On our list of antiderivatives. You can actually also do that one with substitution, but we didn't know substitution. But what about this? That's not on our list of antiderivatives. Okay. The t to the fourth by itself is, right? Like if this was gone, yes, t to the fourth is on the list. And if the t to the fourth is gone, sine t to the fifth, well, actually, that's still not on our list because of the fifth power. We didn't learn about that. We learned about how to do it if the constant's out front, not if it's up as an exponent. So this is not on the list. But the main point is that this function here, this entire function, is not on the list of things we know the antiderivative of. We don't know its antiderivative because it's not on the list. So we don't know it. So you need to recognize that this is not something that you're supposed to know the answer to. And when we do substitution, what will happen is magic will happen. The magic is substitution, so it's not that magic. And after you do the magic, it's going to be something like this. And when it is, that's going to be on the list. Okay, and we're not going to do that right now, but that's what substitution will do, is it will take a complicated integral like this that we don't know how to do. You do the substitution procedure, and it'll turn it into an integral like this that turns out to be easy. All right, details are going to be in the next lecture. So point is, you want to have in your mind that the antiderivatives that we learn here are the only ones that we know. And if your function is not on this list, not in one of these integrals, then we don't know it right now. We don't have a way to do it, okay? So you need something more complicated, a more complicated technique. The main thing is that you can't look at this and say, I already know how to do it. Integrate the t to the fourth, integrate the sine. No, that's not how it works. Okay, so that's it for right now. Talk to you guys later.